Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Srinidhi Ravi with us today. Hello, Srinidhi.
Hello, Frank. Thank you for having me today.
Well, thank you so much for agreeing to talk about your very awesome article, which we'll get to here very shortly. I do have to comment on your background. I think it's a very lovely background picture. What is that?
Oh, this is Myron Middle Dome. This is an oblique image from the Lunar Reconnaissance Orbiter camera,
All
and
right,
it's one of the Silicic domes on the moon. So
which we're going to cover fairly soon. Very good.
exactly, yes.
Okay. And Srinidhi, what is your geolocation?
I am currently in the United Arab Emirates, so in the Middle East.
I think you're the first one I get to do from United Airways, so very good. Let's
Oh,
see, and it is October 15th of 2025 as we record this, and we are past equinox. So, are we getting a little weather change there in the UAE,
uh,
or is it always
minimal
kind of the
change.
same?
No, there's a minimal change in the weather.
Okay.
Yeah, so it was very hot and humid in the summer,
Ah,
and it's less hot, but still very humid.
okay. I can kind of
Yeah.
relate to that. It is, of course, hot and humid, as you know, in Phoenix.
Yes.
But we did have a really big, well, we got the remnants of a hurricane rolling up. And so we got like 4 or 5 days of rain, which is pretty unusual. But it also blew out summer. And so we have definitely landed rather abruptly into our fall mode here. So it's very nice, very cool. Let's see. And Trinity, what do you like to do for research?
I like to study the procellarum creep terrain on the moon, which we will
Cool.
cover shortly. I like to use a combination of remote sensing data and models. Again, we'll be covering some of those shortly, but that's pretty much what I like to do. The overarching theme is to understand the lithospheric and thermal evolution of the procellarum creep terrain.
Very cool. Very cool. And that is going to bring us to this very awesome PSJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. On the origin of silicic magmas on the moon, and Trinity, take us away.
First, I'd like to give a shout out to my co-authors, Christy Till, and she was my mentor for this project primarily, and of course, my PhD advisor, Mark Robinson, both at ASU. And yeah, I mean, could not have done this without them. This project has been a long time coming, so I've been working on it for a while. So
Good shout out.
yeah.
Good shout out. Okay, let's go ahead and roll into it.
So the overarching goal of this project is to understand how silicic magmas were generated on the moon. So essentially, silicic magmas or granites are typically generated in the presence of water and plate tectonics on Earth. Those
Yeah.
are the two key ingredients required for the generation of these magmas. But of course, the moon does not have either of these ingredients, and yet we find rare occurrences of these silicic material.
Mhm.
So how did they get there? That is essentially the question that we're trying to answer. The other thing is that few fragments of these rocks have been returned by the Apollo missions,
Nice.
but none of the landed missions or sample return missions ever visited the silicic target. So our understanding of these domes are, limited to remote observations, and so that's what's motivating this or motivated this project.
Cool. Very
Um, well, I said none of them have visited. I should say none of them have visited yet.
There you go.
That's for the end. No spoilers yet. So um, essentially, there are three geological terrains on the moon. So I cannot talk about silicic magmas without talking about the Procellarum creep terrain,
Okay.
which is figure one.
Okay. And just to let people remind them what creep means, potassium,
Yes.
earth, and potassium, or phosphorus.
Yes.
Okay, and let's
Yeah,
slide down.
potassium, rare earth elements, and phosphorus.
Yes, let's slide
Yes.
down to figure one, and here we go of a global map.
So, what you're seeing here is a global map of the moon. The underlying map is topography from LROC, or the Lunar Reconnaissance Orbiter Camera, and
Uh-huh.
the overlying map is the Lunar Prospector, Gamma Ray Spectrometers, Thorium Abundance Map, and you have the scale bar on the side.
Gotcha.
So the Procellarum creep terrain, which is outlined here in white, is one of three global crustal provinces on the moon. The other being the feldspathic highlands terrain, which is all this stuff here or this region here, and then the other is this South Pole Aitken terrain,
Yes.
which is here. It's like cut off because of the projection, so it's on both sides of the map.
Yep.
So this region it occupies only about 10% of the moon's crust by volume, but it contains about 40% of the total thorium abundance. So
Hmm.
this region is a thermally and geochemically anomalous terrain. So it sticks out like a sore thumb, right? If you look at
Yeah.
the rest of the moon.
Yeah.
And so what you're also seeing on this map is the location of the six identified silicic targets or silicic edifices.
Okay.
The one image in the background is number 2. It's Myron Dome.
Okay. Nice. Thank
And
you. Good connection.
so, yeah, so 5 of these are within the Procellarum creep terrain,
Mm-hmm.
and one is an outlier. This is
It is.
the Compton Belkovich Volcanic Complex, or CBVC, which is
Mm-hmm.
not the focus of this project. We still it's still an outstanding question.
Okay.
So, these landforms were first detected through remote observations. First was from ground-based data, telescopic observations. They showed these regions to be of anomalously high albedo and also strong absorption in the UV.
Okay.
So they were called red spots initially. Then came the Apollo orbital missions, which they did chemical analyses of aluminum versus silica and then magnesium versus silica ratios,
Okay.
and those were comparable to samples rich in creep, which is the potassium rare earth elements and phosphorus.
Okay. Mm-hmm.
Then, of course, came the lunar prospector gamma ray spectrometer, which is the product that you're seeing is this map.
Yes.
And they found that these domes are located in elevated thorium regions. So they're not just within the PKT, but they also have a thorium abundance of around 60 to 65
Oh,
parts
wow.
per million.
Okay. ppm. Yep. Okay.
Yeah, ppm. And more recently, the Lunar Reconnaissance Orbiter's Diviner instrument, which is thermal infrared, detected these concave up spectra, which was consistent with
Okay.
high temperature polymorphs of silica, so tridymite and cristobalite.
Okay.
Once again, confirming that these regions are in fact of high silicic material.
Okay.
Or, yeah.
I'm with
So there are 3 hypotheses as to how these landforms came to be or how these magmas were generated. One is crustal melting. So basaltic magma that is rich in creep, because again, creep is the ingredient here. So creep rich magma intrudes the pre-existing crust that's made of norites and alkali gabbronorites,
you. Okay.
and it partially melts the crust. Not completely, but partially. And that partial melt is typically enriched in silica, erupts to form these silicic domes.
Okay.
The other hypothesis is fractional crystallization. So you have a basaltic magma, again, creep rich basaltic magma that undergoes cooling,
Okay.
And as it cools, your mafic, your more dense minerals would crystallize
Yep.
and sink and then leave behind a residual silicic melt,
Yes.
which is also enriched in thorium because thorium is an incompatible element, and so it prefers to stay in the residual melt rather than get incorporated into crystals typically.
Gotcha.
Um, and finally, the third hypothesis from Blanchard et al. And then of course Hess et al. 1975 was
Uh-huh.
that is silicate liquid immiscibility. Now this is an
Okay.
extension of fractional crystallization.
Yeah.
So when you take a magma and you crystallize it greater than a certain degree, which is 90% is the threshold. So when you crystallize it beyond this limit, the
Yep.
magma then splits into two coexisting yet immiscible melts.
Which,
So immiscible melts. One that is rich in silica and the other that's rich in iron.
okay, I'm with you. Ooh, iron.
Um, the issue with this model, or the inconsistency with this model, is that the thorium, which is this key indicator for silicic magmas on the moon, in this process partitions with the iron-rich melt rather than the silica-rich melt.
Oh,
So it's inconsistent with
huh.
our observations, both in terms of returned samples and in terms of remote observations.
Yes. Okay.
Yes. Um, so now there were some recent experimental petrology studies
Cool.
from Gullikson et al. 2016, where they observed this silicate liquid immiscibility again. So their starting compositions were Monzo gabbro and alkali gabbronorite, which both of which will make a cameo in this work.
Nice.
Um, and what they found was with the Monzo Gabbro starting composition,
Okay.
they were left with a 5% melt enriched with 67 weight percent silica.
Ooh.
So high silica, but very small amount of melts, which is hard to sort of erupt. So there's this question of how do we get such low melt percentages out,
Okay.
um, or erupt them? And the other result from this was that, okay, with the other starting composition, they had 40% residual melt, which is
Ooh.
higher, but
Okay.
then their silica content was 56 weight percent. So it was more on the intermediate side
Okay.
of composition rather than, enriched in silica.
Right. Right.
And what they also found was their thorium. So they
Yeah.
doped these starting composition with thorium.
Yep.
And so what they found was thorium, as the silicic composition was increasing in their experiments, the thorium composition dropped,
Yeah.
which is, again, not what is expected from what we know. So that's sort of the background. So we decided to retest these hypotheses,
Good.
mainly both partial melting, or in this paper, we call it crustal melting,
Uh-huh.
and fractional crystallization. So that's what we did using a model called rhyolite melts.
Okay.
But first, I'd like to go up to the table,
Uh,
so just to orient people with
yeah.
the
Yeah.
starting compositions.
Okay.
Okay, so the first, I think there's like six compositions. So from alkali gabbronorite all the way down to shock norite, those are our crustal starting composition for part one of these models.
This group. Okay.
And then the creep basalts that you see here, the four other starting compositions, they are for fractional crystallization runs that we did. And then finally, the last samples here. These are these are granitic samples
Uh-huh.
returned by the Apollo missions. Well, I should say that all these materials are Apollo materials, but these are the granites returned, and those serve as sort of our anchor points to
Cool.
keep us on track. Hey, we're running these models. Can we match our model composition to the real world data. So
Right.
they serve as the ground truths of pristine granite clast 14321 all the way down to the lunar granite 12013. So that is sort of these are our starting composition that would get input into rhyolite melts. But
I got,
before rhyolite,
I got
sorry, did you
one
have a
question
question?
on, yeah, one question on the
Yeah.
table. Do the triple dots mean that something wasn't measured or,
Yeah.
okay, okay,
They weren't measured, or it was below detection limits.
fair.
It yeah.
Okay,
Yeah.
I'm with you.
Um so before we get into crustal melting, first we need to know if this basaltic magma can actually partially melt the pre-existing crust. Because if it cannot partially melt, then, well, there ends the story, right?
Right.
So,
I know
so
what
if we
you mean.
scroll a little bit, I can orient people with the
Uh-huh.
equations.
Sure.
So equation one is basically our input.
Huh.
So yes. So how much? Well, the thermal, how much thermal energy, or can a basaltic magma really input? And we assume that this is the liquidus temperature. So we assume that this basaltic magma that's intruding the crust is 100% liquid. There are no crystals, and this is just to
Yep.
keep it simplified.
Uh-huh.
And so we know the liquidus temperature of basalt. This is calculated again using rhyolite melts.
Yes.
And we know the specific heat capacity. So that is the first equation. The
Mm.
second equation, and this is, I should cite previous work, Sparks and Marshall 86 and
Uh,
Till et al. 2019.
cool.
And then we need to know how much heat is required to drive this crustal melting. And
Yes.
so essentially, this initial heat of the basalt needs to either equal or be greater than this amount required to drive the crustal melting. So this is the equation that
Okay.
we used. And so T melt, that is for different melt fractions.
Yes.
So the temperature of different melt fractions that we got from rhyolite melts. Um, this is the heat of fusion
Yes.
and the melt fraction again. So that
Yes.
is the temperature of the melt fraction. So T sub melt is the temperature of the F sub melt. So, um, and then finally, of course, the solidus temperature of the crust minus the crustal temperature that we made some assumptions that is in the paper. So I'd like to go to
Okay.
the second figure to
So we're gonna do
um,
that. We're gonna do it, and then there's table two, table three. Let's slide down to figure two. Oh, very nice. Okay, this is the thermal energy required. Mm-hmm.
yes.
Mm-hmm.
So we find that this is the thermal energy required, but the thermal energy from the basaltic magma itself is greater or equal to, it's like within the order of magnitude. So what we find is, hey, okay, so the basaltic magma can actually partially melt
Okay.
these starting compositions at any melt fraction. So 0 all the way up to fully
Cool.
melt.
Yes.
So
Mm-hmm.
yeah, so and these each of those are sort of the intervals, the temperature intervals, the each dot or circle that you see.
Uh-huh.
So yeah, so on the x-axis you have melt fraction. So 1 is fully liquid, 0 is solid, and then you've got your delta H, which is the thermal energy required, times 10 to the 6.
I'm with you.
So, okay, so that is the first step. And then the second was, of course, now we needed to run these simulations on rhyolite melts. I think I'd like to go back to the method section
Sure.
where that is.
Right.
Um,
Red light melts. Here we go.
right. So rhyolite Mel's is a thermodynamic model for phase equilibria of magmatic systems. They're calibrated to petrological experiments on Earth. So
Cool.
they're not calibrated for the moon. So there are some limitations
Okay.
of using this model,
Sure.
which we'll get to in the discussion section. But for now, rhyolite melts rhyolite, and it's also calibrated to silicic magmatic systems
Okay.
rather than mafic magmatic systems.
All right.
So the silicic magmas are thought to be generated in shallow crustal depths on the moon. So what we did was we model these the partial melting and of course fractional crystallization uh, hypotheses or mechanisms
Yeah.
at depths of 1 kilometer
Okay.
all the way down to 10 kilometers.
Okay.
And we calculated the pressure, of course, using this classic equation. Pressure is a function of density, the gravitational acceleration, and of course depth.
Cool.
So
Yeah.
we've got
Good.
our pressure,
Yes.
and we've got our temperature. So we also need to constrain the temperature. So the the starting temperature would be around 850 to 900 degrees Celsius, which is expected of silicic melts. And the ending temperature would be the liquidus temperature of your starting composition, whatever that might be.
You're right.
Um,
Okay.
the other caveat here as well is that so the moon, unlike the Earth, is an incredibly dry environment.
Yes.
So now that affects oxygen fugacity and how that plays into our models. So we set our oxygen fugacity to IW, which is the iron wustite buffer, um,
Okay.
to 2 log units below the iron wustite buffer. And
Yeah.
yes, so representative of very reduced lunar conditions.
Right.
Anyway,
Mhm.
so for the crustal melting model, as I showed in the table above, we had our starting compositions,
Right. Three.
calculate the liquidus temperature. Now, I should say that rhyolite melts, the default program is batch crystallization, which is essentially the reverse of batch melting or partial melting. So it's just the reverse. So you just view your data in the reverse manner, but
I'm with you.
it's the same. And if we go to I think uh, one of the plots
Okay.
that comes after the thermal, I think it's plot number 4, I want to say.
Let's see. Three, maybe?
Oh, yes, sorry, plot 3, yes.
I'm with you.
So what you're seeing here is you have your the partial melting starting compositions are in these circles, and the others we can ignore for now are
Okay.
the fractional crystallization
Okay.
starting compositions. I've just plotted them on the same space so that people can see which model is more plausible or which mechanism is more plausible.
I'm with you.
So we see that the starting composition, some of them, and the grayed areas represent your target compositions, and those are from the moon. So the range of compositions that lunar granites represent.
Okay.
So what we find for panel A, which the y-axis is melt fraction,
Mm-hmm.
and the x-axis is silica,
Mm-hmm.
is that yes, for most of these starting compositions, we're able to match the
Okay.
silica composition at very low melt fractions. So this is less than 10% melt. So 0.2 is, yeah, that is the melt fraction,
I'm
or
like,
20% melt. So they're at very, very low melt fractions. We're able to enrich silica.
I'm like,
If we go to panel B, we see that, okay, as expected, the iron contents are low, because these are
yeah,
silicic magmatic systems, so we expect iron to be incredibly low.
there you go.
If we go to panel C and D,
Okay.
these are our alkali compositions,
Okay.
and there some of them, um, they do there is a strong match. However, the melt percent
Yeah.
for both sodium and potassium, if you add these two up, which is the total alkali, they
Okay.
don't match lunar fragments. So on their own, there is a match, but when you add them up, which we'll see in a plot later on, there is this discrepancy.
Okay.
So this is the results for partial melting, um, uh, corresponding to a depth of 1 kilometer, which is around 42 bars pressure.
Yeah, I
And
think
if we go all the way down to, I think, uh,
yes.
number 9, I want to say, or
Okay.
not, number 8, sorry, figure 8. So figures 3 to 8 are similar. They just represent different depths and different pressure.
I'm with you.
So this is your other end case. So the first one was 1 kilometer depth, and this is 10 kilometers
Yes.
depth,
Okay.
or 417 bars pressure.
With you.
And we see the same trend here, where yes, we're able to match the silicic compositions.
Yes.
Um,
Yes. A
for
little
some
harder.
of these starting compositions,
Okay.
two of those. So this is the brecciated troctolite
That's
and the shocked norite don't match the silica composition.
ooh,
They sort of stand out.
right.
And again, with total alkali, there seems to be total alkali, not individually. So total alkali, there seems to be a discrepancy.
Okay.
Excuse me. But again, potassium, there is no match with most of these compositions. So
Okay.
even though we're able to match maybe, one or two of these compositions, we're not able to match it holistically.
There you go. I'm with
So yeah. And then the second method was fractional crystallization,
yes.
which, sorry, did you have something to say?
No, no. I'm following.
Oh, yes. I So if we go back to methods, I think it's in this
Okay.
part 2 of the method section.
Okay. Let's go slide up. Let me get where I'm at here.
There it
There we
is.
go. 2222 fractional crystallization model. Okay.
Right. So, essentially, it's what we did was we modeled fractional crystallization using a different set of starting compositions. So our creep basalts, there were 4 of those,
Right.
2 from Apollo 14 and 2 from Apollo 15. And they're both enriched in creep materials, especially thorium, which is this, this recurring theme. And again, our oxygen fugacity was set to 2 log units below iron wüstite.
Uh-huh.
Again, our temperature range was from the liquidus temperature of the creep basalts
Yes.
down to 850 degrees Celsius, which
Okay.
is, and then we set that to an interval of 50 degrees. So the two models, we tried to keep it uniform. Of course, the mechanism is different,
Yes.
but in terms of the temperature parameters and the pressure parameters and the oxygen fugacity, they're the same. So then we can have more of a one-to-one comparison.
Yes. I'm with you. Hmm.
And of course, we selected fractionate solids. So then this invokes fractional crystallization as opposed to batch melting or batch crystallization.
Yes. Yes. Yes.
Of course, like I said, the key character in the story is thorium. So we also had to calculate how the behavior of thorium. Um, we did not calculate thorium partitioning for the crustal melting models because these starting compositions lacked the initial thorium. So we need
Yes.
an initial amount of thorium to then map out how the thorium evolves as fractional crystallization progresses.
I'm with you.
What we did was that we used a constant bulk distribution coefficient
Okay.
for our calculations. We did also do a sensitivity analysis, which is in the appendix,
Mm.
where we had a variable bulk distribution coefficient.
Okay.
So for each step, as fractional crystallization progressed, we would have our mineral modes. And so we would recalculate this d sub th, which is the bulk distribution coefficient. And we only found a very small difference between the two methods. So we just
Good.
decided, for the sake of efficiency, we decided to go with a constant bulk coefficient distribution.
Great.
So how did we calculate this? First, if we go down to table 2,
Table two.
we have
Table
our, I
two.
believe,
Yeah, table two is up. Table two
ah,
is up. One and two. Here we go.
okay. Okay, so
Top three, maybe.
table 2 is, this contains the modal mineralogy
Yeah.
of different minerals within these Apollo creep basalts, and all these. I should say that these tables were by and large compiled from the Lunar Sample Compendium,
Hmm.
which is hosted on the Lunar and Planetary Institute's website. It's an incredible source.
Yes.
It makes the lives of scientists or like people doing research very easy. So this is the modal mineralogy. That is step one we need to know. And then, of course, we need to convert these into weight fractions for the calculation.
Yes.
So we did that.
Okay.
And
Okay.
then
I'm with
once you have your weight fractions, um, convert them into weight fractions, and you have your distribution coefficient. So for each of these minerals, this is the distribution coefficient of thorium.
you. Okay.
So they're all less than 1, which means
Quite a bit.
they're less, which means that they're like thorium is generally incompatible with these elements. So greater than 1 means compatible, and less than 1
Thank
is non-compatible.
quite a bit.
And then finally, I think table 4
And with
has the concentration of the thorium within the creep basalts.
yes.
There we go. So this is your initial thorium concentration. So
Okay.
what we did in equations 4 to 6, which is our
Okay.
um,
Vision.
thorium partitioning, is first convert the weight proportions into weight fractions.
Yes.
Then from the weight fractions and then the uh, distribution coefficient of thorium in each mineral, we then calculated the bulk thorium distribution.
I'm with you.
And finally, equation 7, this is where we now model how thorium behaves as fractional crystallization progresses. So this is
Okay.
the initial concentration, the Cl thorium, which is the concentration of thorium in the residual liquid.
Yes.
And then that is the concentration of thorium in the sample itself, which is given in table 4.
Yes.
F is the melt fraction that we have from rhyolite melts.
Cool.
And then, of course, to the exponent is the bulk distribution coefficient. So using this,
Okay.
that we assume to be constant.
Constant.
So using this, we now know how thorium behaves.
Cool. Okay.
Um, it within the magmatic system. And so
Right there.
I'd like to go back to figure 3.
Sure. There we go. There was figure three. This one we covered. Yes. Now
Yes.
we'll do the square.
So now, yeah, so I basically want to draw everyone's attention to the square markers rather than the circles.
Okay.
Actually, we can talk about both in tandem. So the square markers are the starting composition for our fractional crystallization model runs.
Yes.
And we see that there is, again, higher, there's silica enrichment, but at a higher melt fraction compared to the crustal melting starting compositions.
Oh, yes.
And again, just to remind everyone that the grade boxes are sort of target compositions from the Apollo missions
Yes.
to sort of keep us on track. And um, the
Okay.
panel C and D are again to
Hmm. Nice.
see how alkali behaves.
Nice.
Again, the
Okay.
starting composition for the fractional crystallization experiments or the models are more consistent with the Apollo samples.
Yes.
Um, and so this is the model run that represents fractional crystallization at a depth of 1 kilometer. And if we
Yes.
go to figure number 8,
Okay.
we'll see that for the other end member, which is the 10
Deeper.
kilometer depth.
Yes.
And we see that the results aren't really changed by that much. We see this high silica enrichment associated with relatively higher melt fractions,
Both
and
groups.
again the same with alkali. And of course, iron we expect that to be low
So
again. So these are um, high, or they're consistent with the silicic materials returned from Apollo.
cool.
So to tie it all together,
Very cool.
the following figure, which is figure number 9,
Okay.
is
Hmm.
the
Nice.
total alkali silica diagram. It's essentially a classification diagram for igneous rocks, and these are extrusive igneous rocks.
Uh-huh.
So we see that the starting so the this is so we decided to plot up to 10% partial melts and residual liquids,
Okay.
because that is our sort of our threshold. And so if you see the first two compositions, cataclastic norite and
Uh-huh.
alkali gabbronorite,
Huh?
um, so these
Yikes.
right here at the bottom,
Right.
so we're able to match, right, like I said before when we were looking at the other plots, that we're able to match the silica composition, but not the total alkali.
Yes.
So those are still low.
Okay.
And the total alkali compositions are important because if you look at the Apollo fragments shown in black dots,
Yes.
those are very high in alkali compositions. And
Yeah.
that is expected of high temperature silicic magmas.
I'm with you.
So we would expect silicic magmas on the moon to be of higher temperature because of the lack of water and low and incredibly drying conditions. So we would expect them to be higher in temperature, which means they
Cool.
would also be enriched in alkali and thorium.
Cool.
Um, but
Yes.
when we look at our results from the fractional crystallization runs,
Uh-huh.
so the Crete basalt residual melts,
Yes.
those are, plotting closer to the Apollo samples. They're more
Yes.
consistent with the return samples. So
Those right. Yes.
there are outliers, but by and large,
Uh,
they are more consistent with the Apollo samples than
He's
the
down here.
partial melts.
Yes.
Then those four dots hanging at the bottom.
Right.
Um,
Okay. I'm with you.
and I'd like to go to now figure 10, which shows thorium partitioning. Again, uh, we we calculated how thorium behaves within these systems. Um,
Yes.
yeah. So again,
A little bit.
the figure 10, this is corresponding to a depth of 1 kilometer or around 41 bars pressure.
Mm-hmm.
And again, the grade regions represent um, Apollo
Okay.
samples.
Mm-hmm.
So there are two y-axes. The blue y-axis plots the thorium composition or
Mm-hmm.
the thorium concentration,
Yes.
and the red axis on the right is the melt fraction. And
Mm-hmm.
the x-axis is silica composition. So we want to tie silica composition to thorium. So these are the two sort
Okay.
of
Yes.
indicators.
Mm-hmm.
Aside from alkali that we saw in the plot above, figure number 9,
Yes.
but these two, again, we see that, for low fractional melts,
Okay.
so this is 0 is solid rock, and or melt fraction is 0, and then melt fraction is fully liquid.
Yes.
So
Notice reversed.
for
Yes.
very small melt fractions, we see thorium enrichment, and that is expected because thorium, like we said, is an incompatible element which likes to hang out in the residual liquid more than it does in crystalline structures or within the rock.
Yes.
So we see this thorium enrichment
Uh-huh.
across starting compositions. So
Yes. Okay.
high silica and high thorium with around 20 to 30% residual melt,
Mm-hmm.
which is consistent. And
Cool.
if we go to the final figure, which
Yes.
is a
Okay.
similar figure, I should also mention that the KB is creep basalt, and then the four panels represent the four different creep basalt starting compositions.
Yes.
Um, yeah.
I'm with you. Okay.
So
And
if we go to figure 15,
this is the
um,
thorium partitioning. Okay. Oh, I'm sorry. Figure 15.
yes,
Hold on one sec.
uh,
Figure
it's all
15.
good. It's
And so now we're down.
again,
I'm with you. Uh-huh.
yeah. So again, we see that okay, even at a higher depth. So this represents a depth of 10 kilometers, which is
Yes.
corresponding to a pressure of 417 bars, and
Okay.
we see this a similar trend where there is a silica enrichment along with thorium enrichment
Yes.
for about 20%, 20 to 30% residual melt.
Very.
So,
Yep.
so this is consistent with our, the results are more consistent with the fractional crystallization hypothesis
Yes.
versus the partial melting hypothesis.
Okay.
So that is, the overarching conclusion is that yes, silicic magmas can be generated on the moon in the absence of water and plate tectonics along a high geotherm, so higher temperature,
Yes.
low oxygen fugacity,
Yes. Low.
and so that is our conclusions. Now there are caveats here. One is, um, you know, rhyolite melts is not designed to
Okay.
look for silicate liquid immiscibility.
Fair.
So to refresh people's memory a bit, is that silicate liquid immiscibility happens at a threshold of greater than 90% fractional crystallization.
Okay.
So even though rhyolite melts, our models don't look for it or don't calculate that or don't output silicate liquid immiscibility, we don't expect that to be a problem with our models because our residual liquids are less than that threshold. So they're within like 10 to 30% residual melts. So
Okay.
they're less than that 90% fractional crystallization threshold. So
I'm with
even if silicate liquid immiscibility should happen, or even if silicate liquid immiscibility is not output or is not calculated on rhyolite melts, that wouldn't be a problem with our study because we're within that threshold.
I'm waiting. Yes.
And the final thing is that, okay, well, these are still, relatively small melt fractions. How does how do these small melt fractions erupt? And one way that has been proposed in previous work is that there could be a magma recharge. So you have this magma that is, has interlocking crystals and liquid that could be remobilized through a recharge of fresh magma and then allow it to erupt,
Got it.
or eruption through nearby
Double
impacts
pop.
as well.
Oh, very.
And
Hmm.
that um, that it concludes this talk, or well, this paper. That's the conclusion. Is that we're able to generate silicic magmas using fractional crystallization of crete basalts, which we think are the parent magmas for silicic materials on the moon.
Very cool. Very cool. Beautiful work. Beautiful
Thank
work.
you.
Yeah. Awesome. Pull that out. All right. Srinidhi, thank you so much. That was very cool.
Thank you.
Let's see, and you mentioned it, tantalizing hint there in the beginning, and a couple of times as we went through. So let me ask, where do you think we go from here, given the published article? You gave some tantalizing hint about sample returns, but is there additional theoretical work one might want to do on existing samples? Is there additional maybe laboratory astrophysics work that could be done on the equation of state or solubilities or things along those lines? And so where do we go from here, given the published article?
So one is the lunar Vice mission,
Okay,
which is uh, due to launch in 2028, early 2028,
cool.
which is going to visit the Gruithuisen domes. Not this guy, but one not far from this is Myron. Gruithuisen domes is a silicic dome, and so this mission is going to it's a lander, so it's unfortunately not a sample return, and we'll have to wait for a sample return mission
Okay, but
for a while. I'm not sure about that, but it would be the first in situ measurements of a silicic
yes,
target,
cool.
which is exciting. So that is due to launch in a couple of years, early 2028. So that mission would then, test the hypotheses that we presented here, and give us
Nice,
a better understanding of these processes.
nice.
That's one way, and then the other, actually, there's a small maybe paragraph or two that ended up not making it in the paper, and that is lunar or like terrestrial analog sites. So I said at the start of the presentation that, by and large, granites on Earth require water and plate tectonics,
Fine.
to by and large, but there is a small, or there's I shouldn't say small because they are pretty fast, but there are instances of granites. They're called
Uh-huh.
A-type granites, or A stands for anorogenic, meaning did not form due to say plate tectonics, but rather tectonic processes, not plate tectonics.
Uh-huh.
And they those A-type granites are not that dissimilar to lunar granites. They're also high temperature granites.
Right.
They also have high thorium contents.
Oh,
They're also rich in alkali. So that, terrestrial analog studies could be another way
yeah.
to test hypotheses. And of course, there are a lot of people
Cool.
in the lunar science community, petrologists and geochemists doing new analysis on samples that were returned. and papers are, constantly coming out of those. Sadly, I'm not an analytical geochemist or an experimental person, but there are folks out there conducting those studies.
Very nice. Very nice. Well, it's going to be really exciting over the next couple of years as the additional studies are done, as we look at solar analog or Earth and terrestrial analogs, I meant to say, and particularly as a remote mission goes into the late 2020s and early 2030s. Very exciting. It'd be very cool to see.
Yes,
Indeed.
very exciting. Yeah.
Yeah. Srinidhi, thank you once again so much for walking us through your very lovely article.
Thank you so much, Frank. It's been a pleasure.
Sure. And that will do, everyone. And I hope this made your lunar astronomy day just a little bit better. And we will see you on the next one. Bye bye.
Bye bye.